For this part of the lecture, we're going to talk about generative models and learning generative models. So what does this mean? Imagine we're given a data set x1 through xn, which is drawn IID, independently identically distributed, from some distribution which we'll call p sub theta. So thetas are going to be the parameters of this distribution. And then the goal is to output, say, p hat, which is approximately equal, or like tries to approximate p theta. So the idea is, given this data from it, we're going to try to approximate the distribution. Now, this isn't necessarily always the problem. And for example, sometimes we might try to just output, maybe we're not trying to output the distribution itself, but just try to output more samples from the distribution. That might be a goal as well. But at least for today, we're going to focus on trying to learn the distribution itself. I'll note that maybe you don't actually have this this type of assumption satisfied exactly. For example, truly IID data is kind of rare in the real world, but maybe you want to just pretend that this type of thing holds and then see how well you do nonetheless. For example, I mean, when we kind of talked about some modeling interpretations of what say logistic regression means. But in terms of, we know that those won't actually hold, but we're just sort of approximating it as if it did hold. Okay, so that's, in a broad sense, what generative models are, just a data set which is drawn from some distribution, and we're trying to estimate the distribution. Now, let's do a very simple example, which I think we might have already done in this course, actually, but just learning a single Gaussian. That is, we have x1 through xn, which are drawn IID from n mu 1. So just a single univariate Gaussian where we have some unknown mean. And let's just recall what this density function is. This is a distribution which has, it's parameterized, I guess, by mu, p mu of x. So the density is going to be equal to 1 over square root 2 pi exp of minus x minus mu squared over 2. So that is the density of this probability distribution right here. Now the question is, given a bunch of samples from this distribution, can we then estimate this unknown parameter here, the mean? Because I claim that if we could estimate the mean and recover this mean, then actually we'd have then just taking a Gaussian with that same estimated mean, that would approximate the original distribution that the data came from. And yeah, we can do this using our old friend, maximum likelihood estimation, otherwise known as the MLE, the maximum likelihood estimator. And what we do with the maximum likelihood estimator is we pick the parameter which maximizes the likelihood of seeing that data. Or actually, we generally do the log likelihood because that lets us decompose things into a nice sum. So in other words, we let mu hat be equal to the argmax for all mu of the following quantity, summation I equals 1 through n, so sum over all data points, of log of p sub theta of, for now I'll just be more explicit, just p of mu, because that's the only parameter, of xi. Let's expand this because we know exactly what this quantity is here, just plugging in this. So this is going to be equal to argmax over mu, and we're still summing over the points. And what we do is we just take the log of this term. We'll note that when we take the log, then we can decompose it into a few different terms. In particular, if you have a product of two things, then the log of a product becomes the sum of the logs. So what we can do is see that it'll be the log of this term plus the log of this term. Well, notice that in our optimization problem, the log of a constant doesn't really make any difference. So we're just going to ignore this term. So what happens if we take the log of this term? When we take the log of this term, that'll essentially cancel out this x. So this will disappear. And we're left with minus this term inside. And divide by 2. The thing is, again, multiplying by a constant factor will not change our argmax because it's just a constant factor scaling. So instead, we can just ignore that constant factor, and this just becomes minus xi minus mu squared. And now this is a fairly simple optimization problem. In fact, you may just see how to solve this off the top of your head, in the sense that what this does is it essentially chooses it essentially tries to find the point which minimizes the sum of the distances squared, and that's exactly equal to the mean of the data set. That's the maximum. That's kind of the point which maximizes it. So in other words, this can just be shown to be equal to 1 over n summation of xi. That is our estimator mu hat. And if you didn't follow this, you should try it yourself. Just verify this. You can do this simply by just taking the derivative and setting it equal to 0. But moreover, we will also, we'll do this also later, a bit later, to see where it comes from as well. Okay, so, but this is the main idea. Essentially, we did a very simple maximum likelihood estimator to obtain a value mu hat, and if we want to output some distribution p hat, which is close to the unknown distribution, well, all we have to do is output p hat, which is equal to n mu hat 1. That's it. So this is very easy, but there are more challenging cases. For example, what we're going to get into is when we have a mixture model. So a mixture model is a kind of very common type of modeling assumption. And let me write what they are. It might seem a little bit arcane in terms of the definition, but it's actually a pretty intuitive definition when I talk about how we sample from it. So a mixture model is just a density, a probability distribution, and it's defined as follows. Yeah. So again, this looks a bit arcane, but all we have here are, so what we have here, these are just densities. So this is just a probability distribution for component j, because notice that these are indexed by j equals 1 through k. And this here is known as a mixing weight. So the idea is we're going to have a set of k quantities here, pi 1 through pi k, and these are going to be called the mixing weights. And they're going to be essentially a probability distribution over the numbers 1 through k. So pi j is going to be greater than or equal to 0, and summation of pi j is equal to 1. This is the two things you need for a probability distribution. So, okay, this is our density. It's basically a linear combination or a convex combination of a bunch of different probability densities. Right, so let's, maybe this doesn't mean much to you. And I guess let's be clear about what are the parameters of this model. When we have this model, then the parameters are the I sub j's, as well as the theta sup j's for all of these different models. Basically the parameters of each individual model, as well as the mixing weights. Those are all the parameters that we have. Okay, again, like I said, this might be a bit weird. You know, it's a linear combination of these things. I don't find that super intuitive as is. The way I usually think about mixture models is how we sample from them. So the way we sample from them is the following. First, we draw a sample from 1 through k. from the distribution pi. So like I said, that pi is a distribution over the symbols 1 through k. So the idea is, first we sample from this, and that tells us which component we're going to draw a sample from. Are we going to sample from the first thing, the second thing, or through the kth thing? So a very low mixing weight, something which is close to 0, would mean that there's a low chance of getting a point from that component. And if a high mixing weight would mean that there's a very high chance of getting a point from that component. Okay, so the first step, we just essentially choose which component we're going to draw from. And then the second step, we output a sample from E sup j, theta sup j of x. So yeah, it's a very simple two-stage process where we first choose which component we're going to sample from, and then we sample from that component. I think it's relatively intuitive. These are kind of the canonical example that you'll see this used in is when you have, say, multiple subpopulations within one larger population. So for example, let me give an example. I'm not going to draw, I plan to have a picture of this, but I forgot. Let's say the y-axis here, you have a human heights, and here you have frequencies. And so what do we know about human heights? Well, we know generally with human heights that males are taller than females. So this is just on average. So maybe the height distribution for females might look something like this, maybe. And the height distribution for males might look something more like this. And yeah, I drew them sort of at the same height, but really you'd have to sort of sum these two things on top of each other. And so this is basically it's a type of mixture model, maybe if some sort of binomials or maybe Gaussian type data. Well, why do I say that? Well, essentially a frequent model for looking at, say we looked at the height of a male. Well, the height of a male is generally going to be Gaussian distributed. And similarly for the height of a female is going to be generally Gaussian distributed, but there'll be a different mean and variance potentially for each different sex. So yeah, the way you can picture drawing a point from this overall thing is first you pick a point, you pick draw a sample from essentially the mixing weights. So the first choice you make is, okay, am I going to first draw a sample from the male population or the female population, which may be 50-50 in a general human population. And then the next thing you do is you draw a sample from that subpopulation. And yeah, that'll be either something from this distribution or something from this distribution. Yeah, so hopefully that makes sense why this is the type of common modeling assumptions, just to when there's multiple subgroups within the same population. And in particular, learning this as a single Gaussian probably wouldn't work so well. We can't just take the overall mean and the overall variance because that wouldn't give as descriptive a model. That's why we might prefer to model this as a mixture of two Gaussians. So cool. Hopefully the idea of mixture models is fairly intuitive. Is basically trying to draw from many different probability distributions at once instead of just a single one. And that gives us a new mixture. These are in some sense universal ways of representing, in the sense that if you take a mixture of distributions, as long as you have enough different components, then you can model essentially any probability distribution. Now the downside is how many do you need? Often you might need an exponentially large number of components in order to model it. So that's not the greatest in general. Okay, so this is just a general mixture model, and we kind of already hinted at it, but the kind of most common one that's used is what is known as a Gaussian mixture model. And you'll often hear this referred to as a GMM. Now, what is a GMM? I mean, I already kind of informally described one to you right here, so maybe we'll be a little bit more precise. It's okay. I mean, it's not too different from what you've seen before. You could probably write this out yourself, but it's just essentially sum over j equals 1 through k of pi j times the density of a Gaussian. And we'll have a arbitrary mean for this component, an arbitrary covariance for this component, and it'll be the density measured at point x. So yeah, we just take a linear combination of some Gaussian densities. So yeah, let me draw you potentially, I gave you one picture of what a Gaussian mixture might look like, a simple 2 Gaussian mixture. But what more broadly speaking, a Gaussian mixture might look like, it could be something like this, where we have this just space, and we could imagine there's one Gaussian here, and maybe another Gaussian over here, another Gaussian over here. And the idea is you want to find the mean and the covariance of each of these different components. The tricky part, of course, is the fact that you don't really know which sample they're drawn from which components, so maybe you could mix them up somehow. So this might seem kind of familiar in the sense that it looks kind of like clustering, as we talked about in the previous part of this lecture. Well, this is not exactly the same thing. Well, what are some differences with that, I guess, is what we'll try to answer. One difference is the fact that when we were talking about clustering, we were looking at a non-stochastic setting, in the sense that we were trying to minimize, like we assumed the data just was some worst case thing from whatever it came from. Whereas we're kind of making an implicit assumption when we're using a Gaussian mixture model, in the sense that we kind of assume that the data is drawn from something that looks roughly like this, of some form, or is at least close to something like this. So yeah, there's something like a sort of modeling assumption that we make, something about the data set generation process that we make here. The goal is also a little bit different in the sense that before we were just trying to identify the clusters, so just say that this was this a cluster, and then this is a cluster, and this is a cluster, and that was all we wanted. But here we have something a little bit of a stronger goal, something that's well, not necessarily a stronger goal. I guess it depends what you mean by stronger goal, but it's a bit of a different goal, let's say, where we don't necessarily need to find those. We just need to recover the parameters. That is, we want to try to estimate a distribution which will model this well. So for each individual point, maybe we get confused whether this point belongs to this cluster or this cluster, but it doesn't really matter as long as we manage to estimate the parameters of this cluster. We manage to estimate the parameters well enough to approximate the overall distribution, which kind of will generally amount to trying to estimate the parameters of this component right here. So let me comment that this problem would be quite easy if we knew which component each came from. So let's suppose we solved the clustering problem. I'm going to be a bit vague about what I mean by solving the clustering problem. In particular, if we just solve the k-means clustering problem, that might not necessarily be the right thing that we want to do, because that has a different objective function than what we're trying to do. But let's suppose we somehow solve the clustering problem and say we knew each point, which component each point came from. That's a zi. Recall that I'm indexing the points with I. So zi, this is equal to the component that xi was sampled from. So this is going to be a random variable, and it's going to take values which lie in the set 1 through k, because it's a distribution over these points. So it's a random variable. Of course, we don't know this, but assume somehow you magically knew it and somebody told you. Well, then I claim it's very easy, relatively easy to solve this problem. And why is that? Well, we can just once again use the maximum likelihood estimator. So what is the maximum likelihood estimator? Let's just write it again. All we're trying to do is compute theta, which is equal to the argmax over theta summation log of e theta of xi. And this, since we yeah, since we know which components each thing belong to, well, it's easy to simplify this. I'm going to expand this out. So argmax over theta, summation I equals 1 to n. I'm not going to write that in now. I'm going to skip it sometimes when it's implicit. But sum here from j equals 1 through k. And here we have, essentially, we put an indicator in the case where zi is equal to j times pi j n times mu j with j xi. And then we need to close this paren. Yeah. So essentially, what am I doing here? I'm saying that, okay, this is the density. If you ignore this part right here, if you ignore this part, this is just the density of the Gaussian mixture model. But I'm saying, let's just zero out the components from which we knew that they were sampled from. And then essentially just optimizing the resulting function with respect to parameters theta, where theta is going to be equal to mu j, like this is the set of parameters of the model, mu j, sigma j, pi j. Then that gives you the optimization problem which you want to solve. So this would make it rather easy. I'm second guessing my expression here. Maybe we'd have to get rid of the pi's. Either way, I claim that it should be something like this, but it's not too important. We're going to actually derive the real solution. This is a silly solution because we don't actually know the value of what these zi's are. These are sort of latent variables which are not known. But the idea is, if you do this right, then you can use, say, pi hat j, which is equal to the following. So you can take the mixing weight for component j to be the fraction of points which fall into component j. You can also have mu hat of j be equal to, let me write it like this. Let me just write it like this. Let me write a bit bigger, actually, so that you can read it. Essentially just averaging over points in this component. So this is the mean of this component, where we just average them. This should be zi. And finally, we let the covariance for this component, so sigma hat of j, that would be equal to, similarly, this thing right here, the normalization factor. And then times the summation of I equals j. And then we just take the empirical covariance of these points here. Xi minus mu j hat times xi minus mu j hat transpose. So, okay, there's a lot of writing to say, really not too much, but the point is that if we knew which component each point belonged to, well, I claim that is just going to simplify to essentially the problem we already solved, in the sense that when we were doing just Gaussian mean estimation, we wanted to find an estimate for the mean here. Well, all we had to do was take the empirical mean, and that was the best estimate we could get of the mean. So similarly, if we knew which component each point came from, well, then we're essentially saying that, okay, somebody told us that all of these points came from this component. So what we can do is just average them to get an estimate for the mean. And we take the fraction of them which land in this point, in this cluster, in order to get the to get the mixing weight, and similarly take the covariance to get the covariance. So yeah, all I'm saying here is we just decompose it into the different components, and that would be all we have to do if we knew which component each point came from. Now, what makes the problem non-trivial, this would be a trivial problem, but what makes the problem non-trivial is we don't know the cluster labels. So yeah, we don't know the cluster labels, and that's what makes it challenging. Now, how do we get the cluster labels? Well, one way, we can't really get the cluster labels. That's kind of the challenge, or getting the cluster label is kind of the whole problem that we solve. So we could hypothetically get the cluster labels using, say, the k-means algorithm, but that's also not a great solution because, like I said, the k-means algorithm, while it will give you some cluster labels, it doesn't necessarily correspond to the same objective function that we're trying to optimize. So it clusters things, but it's not trying to solve the same problem, so it's not going to necessarily work. Instead, what we're going to do is to sort of alleviate these issues. What we're going to do is have an algorithm which actually learns the parameters and learns these cluster labels at the same time. So what we're going to do is a very well-known algorithm called expectation maximization. Or the EM algorithm. So the way I'm going to describe it today is it's going to be an algorithm which is going to work for Gaussian mixture models, or I'm going to describe it a bit more broadly at first, I guess. But really, it can be used similarly for estimation in any sort of latent variable model. So latent variable model is a very fancy way of saying something like where you draw samples and there's some sort of randomness in the whole process, but you don't see those variables. So the idea of the expectation maximization algorithm is it's going to try to guess what these variables you didn't see are, and then based on the values that it guesses, then we learn something based on that. Okay, so let's but that's getting a bit technical. Let's talk about the EM algorithm. And what are kind of the differences? So I'll comment that this is like this tries to maximize the likelihood of the function. That is, we're trying to maximize something like this. This is in comparison to k-means. K-means is an algorithm which tries to just optimize some like other objective function. So that's one difference. But perhaps the most important reason, the most important distinction of this versus k-means is like it's like a soft version of k-means. That's perhaps like the most important thing you should get across at this point. This is the entire reason I taught you k-means, because of the fact that k-means is a much simpler algorithm than expectation maximization, but it has kind of the same flavor and the same idea. So what do we mean by soft version? So it's a soft version because of the fact, okay, let's talk about why k-means was a hard version. If you remember what we did in k-means we said that each point is going to be assigned to some cluster. That is, point 5, the fifth point in our data set, that is going to be assigned to cluster 3, something like that. Well, in the expectation maximization algorithm, we're going to use instead fractional belongings to some clusters. For example, we can say the fifth point, it belongs 50% to cluster 3, but also 25% to cluster 2 and 25% to cluster 1. So the idea is a point is going to lie in multiple clusters at once, and we're going to use it to compute the parameter updates for multiple clusters at the same time, proportional to how big its weight is. So yeah, it's a soft version of k-means. That's the important thing to get at this point. Okay, so broadly speaking, there's two steps in the expectation in the EM algorithm. I'm just going to call it EM. And the two steps can be kind of written like this, which maybe will seem familiar. So given theta, we're going to assign the points to different clusters. So hopefully this sounds a little bit familiar. For example, if I got rid of this fractionally part, then this would be exactly the second step of Lloyd's algorithm, in the sense that we had some way of assigning points to clusters there. In particular, we assigned them to the points with the closest the cluster with the closest centroid. We're going to do it some other way, based on the parameters theta, which is a little bit more complicated to describe than that one. And the other difference is we're going to do it fractionally. That is, we're going to let a point belong to multiple clusters at the same time, but only in percentages that sort of add up to 1. That's the first step of the EM algorithm. The second thing is, given like our fractional assignment, so given this fractional assignment of points to clusters, then we compute the best data. So you can see, again, this is kind of similar to how we did it for k-means, where we alternate between two different steps. Given theta, we assign points to clusters, and then given these points assignment to clusters, then we're computing the best data. We just keep repeating and repeating until eventually it converges. Yeah, and again, compare this with k-means, where like I said, this is kind of the point where we assign the point to the cluster with the closest centroid. And here, the other thing is, given the fact that we know which, in k-means, the equivalent step would be, given the fact that we know each cluster, which points belong to each cluster, then you compute the mean of each of them, of each cluster, of each component, and that gives you the sort of centroid for that component. So it's very similar. Essentially the only difference is this fractional part and how you compute these things based on the thetas. Okay, so that's the ideas. Let's start to get a little bit more technical here. We're actually going to derive the expectation maximization algorithm, the M algorithm, which is probably the most technical part of the lecture. Okay, so let's recall what our goal is. I'm going to just write it right up here, just so that it's really, let's get a little bit more screen estate here. So the overall arcing goal, which you should always keep in mind, there's going to be quite a few steps before we get to something good for this, but the goal is to try to argmax the sum of the log p theta of xi. So yeah, the maximum likelihood solution. Now, since there's going to be a lot of repetition here, what we're going to just focus on in a number of these simplifications is just we're going to look at this term right here. We're going to focus on this. So whenever, for each of these following lines, you can just pretend this argmax sum is in front of it, but just because that would be very tedious in terms of the writing, I'm not going to make you suffer through that. So let's just start by writing log p theta of xi. Now, what I want to write is that we can break up this probability here using the law of total probability. So this is like perhaps the most important step of this derivation. The rest is all just sort of like manipulating symbols. But conceptually, here's the interesting part. The idea is that this is what we see. We see the data points xi's. However, like I said, there's a latent variable, something which we do not actually observe, and that is these z's here. These z's are the sort of random variables that indicate which component a point was sampled from. So these are kind of implicit in the sampling procedure, but we don't actually observe them. But nonetheless, what we can do is sort of modify our objective to kind of take these into account. So just remember that zi is going to be a random variable which indicates the component that xi was sampled from. So that we're going to use this centrally. So just make sure you get it in your head. Okay, so let's proceed with this. So what we can do now is we can modify this term by just using the law of total probability. And this becomes log sum for j equals 1 k p of theta xi and the sub of I equals j. So what we're saying here is this probability can be written out of the sum of the events that the essentially the point came up, as well as the label of that point is going to be j. Again, this is just the law of total probability. Okay, so where do we go from here? What we're going to do is, it might seem a little bit unmotivated for now, but let me just sort of throw in this mysterious probability distribution, which we're going to explain the role of. So what we're going to do here is we're going to throw in this q sub I, zi equals j, divided by q sub I, z sub I equals j. And then p of theta, xi, zi equals j. So what we did was we multiplied and divided by something. So that's why this is an equality. But what are we doing here? What is this qi zi equal j? Well, okay, this is for now, it's going to be an arbitrary distribution. I claim that this is true. This is always an equality for anything you put in here. But what this is going to represent is this is going to represent the distribution for point xi of what the label of that point is. Remember, each point kind of has some unknown distribution over the labels. Like it could have been zi equals j for any j in 1 through k. But what we're going to do is we're going to define that there is some probability distribution over this random variable, which we don't know. And that kind of is going to fit into this somehow. So you can think of this as being, again, qi is the distribution of zi. And it can be different for each point, for example. Yeah. But for now, it's not too important what exactly it is. It's just going to be something we throw in here, and it can be an arbitrary distribution for now. Good. So let's see. We can do some simplifications. For example, what we can do is we can manipulate this a little bit. I'm going to leave out the sum because the indices, because you should know it by now. Same thing. And what we do is we just sort of group this. This should be p sub theta xi. So there's nothing really hiding here. I just moved this in the denominator here. But now the nice thing that we have here, actually I'll write this back in, is the fact that this is really an expectation of this random variable. When you think of it, this is just an expectation over the random variable zi drawn from the distribution qi. And that's just because, I mean, this is the expectation of a random variable. Like maybe if I write it like this, it'll become more clear. So this is log of expectation of this quantity right here. And this expectation is of, oh, sorry, let me change this a bit. The difference is now we have gotten rid of the summation, so we're not saying zi is equal to j. This is just going to be over zi, where zi is now a random variable and not a realization of it. And this is going to be that zi is drawn according to qi. So just make sure you understand how we took this step. This is really just the definition of an expected value. And if you want, you can just go this way. Maybe it's easier if you go from here to here to see how that happened. So this is just a grouping. And now the sort of step which may be the most unfamiliar to you is we can do this following modification here. And this is going to be the only inequality we use here. We can use what is known as Jensens Inequality. But what Jensens Inequality does is it lets us swap the order of this log and this expectation. I'm not going to get into what exactly Jensens Inequality is, but I feel like I already mentioned it at some point. But either way, hopefully it's not too important for this. Just know that it holds here, and you can look it up if you care. yeah, it lets you swap the order of this log and this expectation. It lets you pull it in. So yeah, because it's a function application and not just like linearity of expectations, you actually have to, it's actually an inequality here. And then at this point, what we can do as a final step is basically expand this out and write it again as an expectation, write it as an explicit sum. So this is equal to summation over, say, j equals 1 to k of qi ci equals j. And let me break up this log at the same time. So we're going to have log of p. Do I want to do this? Yeah, I'll do this for now. I'm going to undo it a bit later, but we'll see. Let me write this here. Yeah, so you can see that we have this expression here, which may be even less interpretable about what we started it with. But okay, let's essentially let's try to recap what we've done so far. So recall our goal was to optimize this. So this was our goal, and I claim we have. You might not believe me, but we've kind of simplified it. Let me this, shrink it a bit. Let me leave it the same size actually, right on the next line. Okay, let's recap what we did for all this work. Well, we basically rewrote this entire expression here. And we showed the following. This is an argmax over theta and qi. And sorry, this is not a this thing. This is an inequality. Okay, so this is what we were trying to optimize in the first place. That is the log likelihood. And what we have done is via the series of transformations here, which hopefully you followed. If not, take a careful look to see if you understand each individual step. We managed to get it to another expression here. Now, this has more things than before. In particular, it has these latent variables which appear in this, which we kind of sum over. Essentially, the main thing is that we threw in is these latent variables that we sum over, and we have probability distributions that we're trying to optimize over to make this as large as possible. Now, let me be clear. In fact, this inequality holds for any possible choice of Q, any choice of this distribution Q. And that's just because, remember when we did this, when we used Jensens Inequality, we didn't do anything special. We didn't need anything special. We just introduced these QIs. But the thing is, if you want this inequality to be as tight as possible, in fact, you're going to want to try to maximize this. And the reason why you want this inequality to be as large as possible is because you're really trying to find the parameters which maximize this. For example, if this inequality is loose, then you're not going to be able to do very well at maximizing it. So yeah, there's kind of two maximizations here. This theta corresponds to this one, and simultaneously this Q is trying to make sure that this inequality is tight as possible. Okay, so I don't know if there's really a good interpretation of what of how to say what this this overall expression here is. I don't think there's anything I could tell you that would be super meaningful, but yeah, we'll just see how we deal with it. Like what can we actually do? How do we optimize this? Well, when we have to optimize with respect to two different parameters, what we're going to do is we're essentially going to use the same idea which I already mentioned to you. We're going to alternate between the two. So we're going to alternate between optimizing, holding theta fixed and optimizing the QIs. And then we hold the QIs fixed and optimize the thetas. So those are the two steps we're going to do, and we just alternate between them until we are kind of done optimizing in the sense that it's converged. Okay, let's move on to the next page, and I'll just keep this at the top because this is our goal. And let's discuss how we're going to optimize this sort of step by step, just by swapping between the two. Okay, and there's kind of two steps, the expectation step and the maximization step. So let's kind of write them down and derive them. So the E step, as we'll call it, is going to be when we fix theta and then we optimize the QIs. So what does that mean? Well, I mean, I guess it's kind of clear. What we are going to do is we essentially just keep this theta fixed and we try to optimize the rest of the expression. So let's see what that is. Let's start with this. Where did it go? There it went. Let's paste another copy here. Okay, so what do we need to specialize this in order to optimize the QIs? Well, really what we're doing is just getting rid of this essentially, because we're only trying to optimize these. And notice that we're optimizing over distributions QIs, because the QIs they're mandated to be probability distributions. That's kind of how we define them. QI is a distribution for the point xi about what its latent variable zi is going to be distributed as. So, right, what can we say? How are we going to simplify this? Well, okay, the main thing that we're going to do, there's kind of two steps here. The first step is basically just to shrink this a little bit. It's just to break this summation up, or break this up. So what we can do is write this term here as essentially a conditional term. So what we're going to do is we have, this is just the joint density of both of them. So that's the probability that we see xi and that zi is equal to j. So one way to write this is as follows. What we can do is instead just write it as zi equals j conditioned on xi, and then within this sort of thing here times within the log here, times p of theta of xi. So this is one way of writing it, and this is just using, I don't know, I'm not sure what the name for it is, but just a standard rule of probability. But since, remember, we're taking the log of this product here, so we can always break this log into a log of products into a sum of logs. So yeah, let's do that. So essentially what that'll be is, let me just make it clear that this is here. What we would get here now is summation over, again, j equals 1 through k of q sub I, the I equals j times p of theta, log p theta of xi. So now what's the, and then close parens over here. Okay, what's the key thing to note about this term here at the end? Well, the key thing to note is that it doesn't really show up in this optimization here because of the fact that this is just going to be some constant which doesn't depend on these QIs. And since this is a distribution, when you sum, so you can pull this out of the summation, and this summation, since QI is a distribution, this will just become 1. So it's just 1, and then this is a constant, so it doesn't show up in our argmax, or it's not relevant to our optimization really. So really we can just ignore this entire term entirely. So okay, we're going to essentially drop that term. And now the sort of final step here is that we are going to argmax over distributions qi. We're going to write this as the following. Summation. Let me be more clear here. We're actually only going to do this optimization over, since this is distribution qi, we're just going to be looking at the ith point. So in fact, you don't have to worry about the summation over the i's, because we're only looking at the ith distribution, and we can do this independently for each one. So let me just, we can just focus on point I. And then here what we're going to have is, again, from j equals 1 through k, qi ci equals j, times, we're just going to regroup these logs together. And in fact, let me change it to be a min. Yeah, so what I'm going to do is I'm changing this to be a min by negating the entire expression. But when you negate the expression, then this will be plus log qi, and then this will become minus log p theta phi. So in other words, this just becomes qi ci equals j divided by p theta of ci equals j conditioned on xi. Good. So hopefully you see where this came from. We just negated the thing so that this became a plus and this became a minus. And then we grouped those two terms together using standard laws of the rule of logarithms. And now the nice thing about this expression right here, this term right here, this is known as the KL divergence between qi zi and the distribution p theta of zi conditioned on xi. So good. This what is the KL divergence, you might be asking? Well, the KL divergence is a common way of measuring distance between distributions. So it's kind of read as the KL divergence of qi with respect to p theta. It's a non-symmetric thing. You'll notice if you swap the locations of p theta and qi, it's not necessarily the same thing. So it's an asymmetric measure of distance. And it's a common one that's used with probability distributions. So this is, importantly, it's going to be non-negative, is greater than or equal to 0. And in particular, it's equal to 0 when these two things are equal. So in particular, this is kind of an if and only if. It's going to be this when this equals to p of theta ci given xi. So, right. What are we trying to do? What did we just show? Let me just write one more thing. So the argmin over all distributions is basically going to be equal to p theta of zi given xi. Sorry, okay, so now let's see what exactly we did here. We did some calculations, but let's recall what our goal was so we don't get too lost. So our goal here was to really say, okay, we are fixing the thetas, so that is we fix the parameters of the model, and we want to optimize over the QIs. That is, we have to find, going back to our analogy with k-means, this is the part where we're fractionally assigning points to these clusters, and we're fractionally assigning points to clusters by defining these Qs, because the Qs are kind of the distribution over the labels of the which cluster that the points belong to, but it's all fractional, remember. Okay, so what we said was we're fixing this and we're optimizing over QIs. So here's our objective function that we're trying to optimize. And again, we hold one fixed and we try to optimize the other, and you do all these steps. And what you do is you arrive at this KL divergence expression, and we find that the solution which really optimizes it is going to be having the Qs be equal to these conditional distributions. So this can be read as given a point xi, what is the distribution of its label? So yeah, we'll revisit this a bit more later when we talk about how to actually compute this, but yeah, it essentially, this is something we can actually compute, really, given the parameters as well as the data points, which is exactly what we wanted. We fix the thetas, we have the x's, and then therefore we can optimize the q's. Okay, so that's the E step, the expectation step, and the other step is the M step. Well, in this step, of course, if the other case we fix the thetas and we optimize over the QIs, here we're going to fix the QIs and optimize over thetas. And specifically, we're just going to look at the same expression again. Let me just copy paste it one last time, and then we can see what we can chop off. So, okay, what we're trying to do here, this will be a little bit of a shorter derivation for now. What we're doing is we have the QI, so we're considering those fixed, and we're optimizing over the thetas. Okay, now importantly, when we're optimizing over the thetas, note that this term here, this entire expression over here on the right, this doesn't depend on theta at all. We can change theta all we want, and this value will not change no matter what. So therefore, we can just totally ignore this term over here. And that's it. This is basically the optimization problem we have to solve when we're doing the M step. Now, this might not seem like great, but this is often solvable in closed form. And we'll see that for GMMs. So what we've talked about so far in this EM algorithm, there was nothing actually specifically that I used which was specific to GMMs. This was sort of stated as a broad latent variable model. Oh, whoops, I'll clean that up later. Yeah, what am I saying here? I'm saying that essentially this nothing about this depended on GMMs. This was just broadly speaking for any points where we don't know these ZIs, but there's kind of some distribution over ZIs, any sort of latent variables. So let's see what this looks like when we actually specialize this for GMMs, and we'll do some calculations with GMMs and call it a day. So, okay, let's specialize this for GMMs. Sorry, one more thing before we get to the actual thing. Let me tell you what the algorithm is, because I haven't really specified it. Maybe it's implicit, but the actual algorithm itself is right here. It's very succinct. The algorithm is initialize parameters. And then we run an E step. Then we run an M step. And then we repeat until it converges. So you can see how similar this is to the k-means algorithm in the sense that it's really initialize and then run 2 steps until you get sick of it or it converges. Cool. So this broadly works for general latent variable problems, model problems in a broad sense, but let's talk about how to specialize it for GMMs. So all we have to do to specialize it for GMMs is really say what this E step is, because we sort of left it maybe a little bit arcane or abstract here. So let's try to specialize what the E step is. And then this M step, we didn't really simplify it at all. So we'll see that. So what is the E step? So the E step is not too bad. So remember what the E step says is that we assign that these QIs, that is the distribution of ZI, we just define it to set it to be the following: P theta of ZI equals J given XI. This is essentially the same thing that we wrote above. And we can simplify this actually a little bit more before we use the fact that this is a GMM. So what we can do is P sub theta of ZI equals J and XI divided by P sub theta of XI. So this is just using a similar probability fact that we've used before. And now this is where the first time we will use the fact that it's a GMM in this derivation. And it's fairly simple to compute both of these expressions here. So this just says, the numerator says, what is the probability that given these parameter models data, that we see the point and it's generated from component J. So this is easy because it's just literally the probability that comes out under component J. So this is like kind of the this is literally just the probability that comes out of component J. And then the other thing is just we can sum over all. This is just the probability it comes out at all. And this is just similar how we would do a density of any sort. We just compute the probability under it. And this is it. So that's easy. This QI, you can see how this is not too bad to compute for each individual point. Another way of seeing this is you can see it as you compute the probability that came out from each component, and then you just normalize that in order to make it into a distribution. Yeah, that's it. Okay. Right, okay, so that's the E step. And you have to compute this for every single point in the data set. For all xi, and also for each of these, you have to compute it for all j in set 1 through k. And then once you have that, then you have all these parameters here. Okay, so that's one thing. And then the M step is the other part, which we will not do in full. What we're going to do for at least the lecture, just to simplify it, we're going to simplify and focus on the case where it's just a 1D and the variance equals 1. Therefore, the resulting model would be something more like p sub theta of x is equal to summation over pi j times, yeah. So this is a bit simpler just for the sake of not making this lecture take 2 hours long. But yeah, what is the M step? Let's compute it. So what are we trying to do? Let's take a look and just copy paste it just for so that you know I'm not trying to pull a fast one on you here. So here's what we got, and essentially all we do is just substitute in the expression for the PDF here essentially. So let me just paste the same thing again. So yeah, all we're going to do is substitute this in. And this becomes yeah, because notice that this is the probability that came from component J and that we saw xi. So this is just going to be log of pi j times exp of minus x I minus mu j squared over 2. Times some normalization factor, of course, which I'm going to leave out again because for reasons there's like, yeah, 1 over square root 2 pi, whatever. But for similar reasons as before, we can just ignore that as we did before. So this can be decomposed a bit into the following. And we have summation qi equals j Now let's just break this up into two different parts. So this becomes log of pi j minus xi minus mu j squared over 2. And now you can see that we have a sum of two different terms, or a difference of two different terms. The first part depends only on the pi's, and the second part depends only on the mu's. So remember, we're trying to do an optimization over the two different types of parameters, so we can kind of focus on each of them differently. So let's do them each one by one. Let's first focus on the mu's, because those are perhaps a little bit easier. We don't have to do Lagrange multipliers. So what we're going to do is compute argmax over mu j's, over the mu j, yeah, of what is it? I guess let's make it into an arg min by getting rid of the negation. So we have summation of qi equals j times 1/2 squared. So this is just looking exclusively at this term, where we don't care about this because it doesn't depend on mu j for now. And then what are we going to do? We do the same thing whenever we want to optimize, and this is a simple convex optimization problem. What we just do is take the derivative. So if we take the derivative with respect to mu j and we set it equal to 0, we will get the following. So what do we get? We get like summation. This is going to be I equals 1 to n of minus qi di equals j times 2 times this will cancel out, but xi minus mu j, and we set this equal to 0. So what I did here was this arrow here, I didn't really specify what it is, but really this is just taking the derivative with respect to mu j and setting it equal to 0, because we're trying to optimize and find the mu j which optimizes it, and this is what we get. And we can just rearrange this, namely by what is it? Moving this mu j over to the other side. And essentially, if you solve for this, you get mu j is equal to, the optimizer is going to be equal to the following. Summation over I equals 1 through n. So this type of thing. Now, you'll notice that this is actually quite an interesting expression, and it's actually easily interpretable. So if it was just, pretend these were all, say, ones or zeros. If so, then this would essentially be an average of some xi's, namely the xi's who belong to this component j. Now, what we're doing here, since we have sort of fractional belonging to different points, to different clusters, instead, you can see that we're kind of taking a weighted sum of the points. So this is sort of the fractional weighting of the points such that they're in the set, and then we normalize by the total weight assigned to these points, that these points assigned to this cluster. So yeah, this is an easily interpretable expression as the weighted sum of points weighted by these belongings to this cluster. Okay, so that's the easier one. Let's do perhaps the trickier one, because it kind of has a constrained optimization problem. So what we did before was we focused on the mu's. Now let's focus on the, instead, let's focus on the i's. And this is what we do here. Let me get rid of some of these things we took along with us. Yeah, whatever, that's fine. I don't know how to make this smaller. Okay, whatever. Anyway, so this is what we have here. We are now trying to optimize this over distributions pi j. So that is, sorry, let me just say distributions pi. So that is, we want to basically optimize this expression, where this I equals 1 to n, j equals 1 through k. But because it's a distribution, we have the additional constraint such that summation of pi of j is equal to 1, where j equals 1 through k. So this is an additional constraint that we have on the optimization problem. So what we can do is we can just use Lagrange multipliers, or maybe we haven't covered them in this class before, but this is essentially the same thing as the KKT conditions that we've discussed. So this overall problem is equivalent to the following problem. You just take essentially the same thing, and then you add on to the function here plus lambda times sum of pi j minus 1, and you're trying to optimize over this new thing. Maybe you have to optimize over this. So okay, that's the new expression we have. So let's make a new page, and in fact I'll copy paste this just so we have it on hand. So this is the expression we are trying to optimize. Move this up. This is the expression we're trying to optimize, and we just optimize this the same way as we always do. That is, we're going to differentiate with respect to pi j. So d by d pi j. And what will that give us? Well, if we differentiate with respect to pi j, then a bunch of these things will kind of disappear. Let's see, any term, the summation will disappear because we're only going to be looking at term j. So we'll have this, we'll have qi of zi equals j, and then we have divided by, since we take the log, it becomes this, pi j, and then we have plus. Here we have, this is just going to be plus lambda, since most of these terms will become 0 when you take a derivative, except for the term which is indexed by j. That'll just be become a 1, so we have this. And then we set it equal to 0. Okay, and now just rearranging this to solve for what lambda should be, or sorry, what pi should be. This gives us that pi j is equal to, what is it, minus 1 over lambda times summation from I equals 1 through n qi zi equals j. And okay, so this might seem like a weird expression. We have this lambda, we don't even know what this lambda is, and we have these things here. Well, the way we're going to get rid of these lambdas in a second, and the way we're going to do that is remembering our constraint. What do their constraints say? It says that if we sum up these pi j, that should equal 1. So this implies that summation over lambda, this right here, this should be equal to, sorry, this is from j equals 1 to k. This is going to be equal to minus 1 over lambda times summation over I equals 1 n summation j equals 1 through k of qi zi equals j. Now, what do we know about this? Well, we know that, let's see, this expression here, remember this is a distribution, so this is going to be equal to 1. And therefore, if you sum 1 over n different points, this is going to be n over here as an expression as a whole. So this is going to be equal to minus n over lambda. However, recall also what this equals. This term here is also supposed to be equal to 1. That's the constraint that we are imposing because it's a distribution. And therefore, this implies that lambda has to be equal to minus 1 over n, or sorry, minus lambda equals minus n. Yeah, that's it. Okay, so what do we do with this? Well, remember our expression for pi j here. Well, we're just going to use this to give our final expression for pi j. So pi j is equal to 1 over n times summation of 1 equal 1 to n qi ci equals j. So, okay, we did all this work, and let's try to summarize what we've arrived at. Remember, this is the m step. So this m step, what we did was we were essentially saying, okay, suppose we have these sort of fractional belongings of each point to these various components. And what we're going to do is find given these belongings to each component, we're going to find the parameter vector theta, which makes sure that this is as likely as possible. And so what we did was we just did the usual thing we do. We sub in the density, we took some derivatives and set them equal to 0, and we got an expression for mu j, which we said has a very intuitive interpretation as like a weighted sum of the points, depending on their belonging. And similarly, we have these pi j's, which tells us the mixing weights, and it's also got a very similar type of interpretation, where you can see it's kind of, if these were zeros and ones, then this would be the number of points which belong to this component. But since not, you're kind of computing the fractional belonging over the data set of points to this component. So try to think about these expressions and see how they're really quite intuitive if you really understand this idea of fractional belonging to different components. So yeah, that's essentially it. What we do is, we initialize the algorithm, then we compute this expression here and assign these to the qi's. And then we compute these values for the parameters, for the mu j's and the pi j's, and then repeat those steps many, many times. And if we do that, then that's the algorithm. And let me show you a picture of what it might look like. It's pretty similar looking to k-means, really. Here is the picture of what the algorithm might look like. So initially, we start with say we initialize the parameters, the mu's and the means and the variances somehow, and perhaps just start over here. And what we do first is we compute the belongings to these different components. So again, it's kind of fractional, but in the picture it's just drawn as red and blue binarily. So yeah, essentially we find that these points over here closer to this one are perhaps assigned to this, and the red points, the closer points to this one, are assigned to this. And then from these belongings, then we can compute new parameters and see that it'll give us covariances that look like this. Now, the thing is, this is of course not the best clustering, but if you run a few iterations of it, you'll see that gradually these covariances shrink and shrink, and eventually we get the kind of correct distributions. Again, so think about this. This isn't exactly what's going on because of the fact that the way this paints it, it looks kind of a lot like k-means. But really, you can think of each of these points as belonging fractionally to the two distributions, and that's more realistic as to what happens. So yeah, this is the EM algorithm applied to Gaussian mixture models. The EM algorithm, like I mentioned, is more broad than just for Gaussian mixture models, really any latent variable model. So yeah, keep it in mind. It's not the perfect algorithm. In particular, it runs into some similar challenges as the k-means algorithm. It might not give the best answer overall, but nonetheless, it's probably the most used algorithm in practice. Cool. So yeah, that is today's lecture on generative models, unsupervised learning, k-means, and expectation maximization. It's a lot of different topics today, but these are all very important, so I hope you learned something.